Okay, I apologize. All right, there we go. We should be live now. Okay. All right. So thank you all for bearing with us. Sorry for being a couple minutes late here. Yeah, so we're super lucky to have Dr. Ahrens with us here today, and I'm going to let Dr. McBride say a few words to get us started. But first of all, thank you, Dr. Ahrens, for coming.
Yes, thank you, Ellie, and thank you, Dr. Caitlin Ahrens, for being here and going to give us a wonderful talk for our speaker series here. Our Faces Physics speaker series is actually sort of brainchild of Ellie in the beginning, and it's been going on since what, about November now of 2020, right? So this has been a pretty good speaker series, and Ellie's done a great job of organizing it along with some of our other SPS members, and we hope to continue it after she graduates here. So this is kind of a little bit of her legacy for the Society of Physics students. I would definitely like to thank Marshall University and the College of Science and the Physics Department. They have always been very supportive of anything the Society of Physics students does. And I really appreciate them advertising all the things that we do and just always giving us support in any endeavors we try to do. So I want to thank them. Of course, thank Ellie for all the hard work she's put into this series, and also thank the West Virginia Space Grant Consortium. They are helping to sponsor this speaker series as well. So if there's students out there that are interested in physics or interested in some of the topics that you hear tonight, or just have a passion for physics, in any area of physics, shoot me an email, look up information on our physics website. So our physics website, www.marshall.edu/physics, you'll find a wealth of information about our physics department there. We have a pure physics track. We have different areas of emphasis. So if you're interested in physics, but also interested in chemistry and biology, or maybe even a medical imaging or computer information technology, we actually have tracks specifically designed for students in mind. Marshall University is an R2 institution, so we do have a heavy research component. There's about 2,500 grad students and about 11,000 undergrad students. Our major, out of all the majors that are available on campus, it's very easy to get a minor from almost any branch on campus. Specifically for the College of Science, it is very easy to do a double major. We have professional advisors to help students with any type of double major combination they would want to choose, as well as any major. So kind of helps keep students on track. So if you do have any questions, you can shoot me an email at mcbrides@marshall.edu, and I'd be happy to try to get you pointed in the right direction if I don't know the answer to your question. So with that, I'm going to turn it over to Ellie. And again, thank you, Dr. Ahrens, for your time tonight. I'm sure we're going to hear a wonderful presentation.
Yes, I'm sure we are too. So, and first of all, thank you so much for the kind words, Dr. McBride. And I do want to make sure to give a shout out to Jackie Sizemore, who was also absolutely instrumental in getting this program started, and to Peter Burberry, who's going to be continuing it on and has been working with us already. So we're super excited for that. Okay, so I just wanted to get started by thanking everyone who's listening for tuning in tonight. I know this talk is going to be super exciting. I'm really looking forward to learning about volcanology in the solar system. I know Dr. Ahrens is going to do a great job telling us about it. So I'll be introducing here in just a second, but before we get started with that, I wanted to mention just a few quick notes just about how the presentation is going to work and future events. So after the presentation, if you were able to come to previous talks, this is the 8th in the series, the first one for this semester, so that's pretty exciting. So you may remember, if you've come to any of those talks, that at the end of the session, after the talk is over, we take questions in the chat. So if you have questions, you feel free to type them at any time, but we probably won't answer them until the end. But we look forward to hearing any of your thoughts or questions or things that come to your mind. In addition to that, if you want to share your questions or your feedback on Twitter, you can tag us at MU Physics Club. So if you do enjoy this talk, hopefully you'll join us for future talks in the series. We plan to have one in October, date and details to be announced. But just keep an eye out on our social media. If you're on our mailing list, keep an eye out for new emails. And we'll be sure to let you know the next event that comes up. So yeah, so now it's absolutely my pleasure to introduce Dr. Ahrens. So Dr. Ahrens is from West Virginia, like me. So I think that's really cool. As she is a West Virginia University graduate. She received her Bachelor of Science in Physics, Astrophysics, and Geology and in 2015, and got her doctorate in Space and Planetary Science at the University of Arkansas in 2020. She's currently working as a NASA Postdoctoral Program Fellow at the Goddard Space Flight Center. And her research focuses on remote sensing of icy surfaces and volatile interactions, including permanently shadowed craters at the lunar poles, focusing on the composition, phases, and thermodynamics of gases. Her specific expertise focuses on modeling of thermal phases of ices and applications to geomorphological and geophysical data on icy surfaces, including the compositions and rheology of Cryovolcanism, and I apologize if I'm butchering these words. Dr. Ahrens also works on a number of planetary volcanism projects, including lava flow morphology, caldera formation, and rheology on Mars, Ceres, and Pluto. Dr. Ahrens is currently applying LRO Diviner data with a myriad of other remote sensing data to investigate volatiles at the lunar surface. So that is a lot of cool stuff, and I can't wait to hear a ton more about it. So we're just really thrilled and fortunate to have her join us here this evening. So I'm delighted to be able to turn things over to her right now. So again, thank you for coming.
Oh, thank you so much for that lovely introduction, Ellie, and thank you so much for the opportunity to chat about ice and cryogeology of the solar system. It's so fascinating that whenever I give talks and they're like, oh, you're just going to talk about ice? How exciting is that? Like, really, I could just go down to my freezer and get an ice cube and that's ice. Like how exotic is that really in the solar system? But that's just it. It's not just water ice, and it's not just a cube that you could put in your drink and make it cold. There's just so much physics involved with it. And so it's my presentation tonight, which I hope I am able to share correctly, and hopefully you can see my slides. Great. Awesome. All right. So yes, going through just the wild and wonderful cryogeology in the solar system. So just a little bit about the background of ice. So bear with me. So most of what I'm going to be talking about is in the outer solar system. So what we consider to be the outer solar system is where the H2O water ice condenses. We call this the frost line or the snow line, but at this line, it's around 5 AU distance from the sun. So at this point, water becomes frozen solid, and whether it sublimates and whether it evaporates, it does all sorts of really cool geology from then on out. Not to say that there's not ice, plenty of ice here on Earth, and certainly on Mars, and a little bit of the moon, and a little bit on Mercury too. But a lot of what I'm going to be talking about tonight is at the Jovian moons and beyond. So, like I said, it's all sorts of water ice is the most abundant ice that you have in the solar system. Now, the weird part about this is that there's actually 19 crystalline types of H2O. And I have a hard time even remembering what the temperatures and pressures are. I have to constantly look at like a reference map and whatnot. But now you're probably thinking it's just H2O. Like, how in the world could you even have different kinds of crystalline structures, though? So how I like to imagine how the H2O even behaves 19 different ways is like you're having your two hydrogen and your oxygen molecules do different yoga poses. And that's essentially what you're doing with your different crystalline types, how they are arranged with each other, and then how do they move on a very small molecular level. And all of this level, all the yoga poses of water ice depends upon your temperature and pressure. So this is the type of reference map I'm talking about. It's called a phase diagram. This is what I look at on a very regular basis for my job. And you may be going, yeah, pretty colors or some Roman numerals there, you know, what's to it. But I only pay attention to essentially the left side of this diagram. The higher up and to the left you are on this diagram, you're dealing with more high pressure, low temperature ices. This is typical of our ocean worlds, and I'll get more into like what is considered an ocean world later. And then the lesser pressure that you have, the more of the surface, icy surfaces that you have with a lot of these moons and planets and dwarf planets. And it's not just water ice either. So I love carbon monoxide ices. I think they're awesome. Methane, ethane, nitrogen ices are really interesting. Carbon dioxide is also a very large component of ices in the solar system as well. And notice here in the blue, I typically work in Kelvin. Some other planetary people work in like Fahrenheit and Celsius though, but I deal with cold temperatures. I deal with like down to 10K temperatures. I'm not going to deal with Fahrenheit at this point. So I pay attention though that all of these different kinds of Kelvin temperatures here, they all have different freezing points, in which case that means just the amount of ices vary across all the different kinds of moons and planetary bodies in general in the solar system. You're not going to get frozen ethane at Mars. It does not get that cold enough, but you can have ethane at the Saturnian moons and beyond. Carbon monoxide, you don't really get much of carbon monoxide ice until you get to around Uranus and Neptune, and certainly at Pluto. So all of these different kinds of ices can interact differently. You have different chemistries. It's just so fascinating. So most of what I do though is looking at not just the atomic level of these ices though, but essentially making ice bend itself like rock. How does it form mountains? How does it form glaciers? How does it form volcanoes? These very large structures that we see all the time with rock and plate tectonics here on Earth. But we see very similar or even dissimilar things, very unique features in the outer solar system, but with ice and no plate tectonics. So how do those even form? So like I said, it's just very, very broad spectrum of planetary science. I specifically look at rheology, morphology, geophysics. I love thermodynamics and a little bit of mineralogy. I do know quite a few colleagues who specifically just look at the chemistry of ices and like the irradiation. Irradiation could also follow into astrophysics. If you want to go the astrobiological route, you would do biology and chemistry. If we wanted to go to a certain moon and actually explore these moons, land something on one of these moons in the future, which is very soon actually, then we're going to need to know the engineering aspect of these ices. What kind of instruments would we want to have to study these ices? So that would be engineering. So I'm just going to give a quick little example here of just how wild and how quick in communication we need to be when studying ice. So this is just a small little subset of Pluto. This is the northern lobe of Sputnik Planitia. And notice that this is all ice. None of this is rock. All of this is ice. You look like you have some chunky ice off to the left there. You have some swirling ice in the center. Okay, so we know it's ice. New Horizons got to Pluto in 2015 and it had a spectrometer on it named LISA. So the LISA instrument was able to give us like, okay, where's the nitrogen? Where's the carbon monoxide? Where's the methane? Okay. So with that lobe, we're seeing a lot of carbon monoxide and a lot of nitrogen. Great. Okay, so we kind of know where all the pretty ice is on Pluto. Now, how do you recreate it in the lab? So there's only a handful of laboratories around the world that can specifically do ices this cold, specific for Pluto studies or even outer solar system studies. So just trying to figure out what kind of ice mixtures can you make, what kind of spectroscopy can you do in the lab? And then from there, can you compare spectra that we got from New Horizons to spectra you get in the laboratory? Does it match? Does it not? And then we look at phase diagrams yet again. So similar to the water ice phase diagram I just showed a bit ago, in this case, this is the methane nitrogen binary, meaning just the two mixtures. And then what do those do? So a little bit of nonsense here. All of the shaded region is all the different kinds of phases we can expect at Pluto. Goodness gracious. Okay, so you're dealing with beta nitrogen, you're dealing with alpha nitrogen, you're dealing with whoever decided to do methane 1 versus 2. Don't know why they didn't do alpha and beta there either. Why not? But all of these different phases, that means, again, you're dealing with different yoga poses of the atomic structures of methane and nitrogen, and then you mix them together, we're going to get all sorts of wibbly wobbly stuff. But again, all from that experimental work, then how do you model it? What makes the ice swirl like that at Sputnik Planitia, especially at Pluto in very low temperatures? From the lab work, can we get a sense of viscosity or density out of the ice? Or vice versa, can you model the ice instead? And that way we can predict how the lab work is going to work. So in a sense, all three of these things is the perfect trifecta of planetary science. You got your mission data, whether it's an orbiter, a flyby, a lander, a rover, whatever. You got your experimental research, and you got your modeling. All three of these need to talk rapidly to each other because we're all constantly sharing research though. So when it comes to ice, it truly is just a constant network of who's modeling what, who's experimenting with what mission data do we have or lack thereof, which is very true in the outer solar system, unfortunately. There's a lot going on at Jupiter. We just mourned the anniversary of the Cassini mission just a few days ago, and New Horizons is still going, but it was just a flyby at Pluto. It didn't stay there very long, so it's still going, but that's about it. Otherwise, before all that was Voyager in the 1980s. That's about it for outer solar system missions. And now to make it even more confusing, ice isn't just a solid form and go, look, it's ice. Okay. Ice could also do some other weird stuff, such as clathration. So clathrates, imagine, if you will, a water ice solid cage. And this cage is actually housing some sort of gaseous vapor inside of it that's just bouncing around inside of this water ice cage. Now, typically clathrates have a methane gas trapped inside of it. It's just bouncing around, wanting to get out, and it's trapped. Now, methane clathrates we actually have here on Earth. They're very prominent in Alaska and certainly in Siberia areas. They get really trapped around like water lines and gas lines as well. But they are possible on Mars, and they're certainly possible at other icy bodies as well. But this is a picture here on Earth as far as like what these clathrates look like. So they look like little lava bubbles, lava lamp bubbles, but this is just how porous all these clathrates are. Now, clathrates in the lab can get very entertaining because of that methane still being a gas and it's wanting to be released. You could also light them on fire, and these are considered to be an interesting form of ice that you light them on fire and they won't immediately melt because the methane reacts immediately to that heat and it encases then the water ice and it just burns off. So the water ice in turn then just gets to hang out and just be a solid block of ice while the methane is getting all heated up and released and vaporized. So lab safety first, everybody. And then you have tholins. Now, tholins were coined by Carl Sagan, and tholins were hypothesized to be on Titan. And lo and behold, there's plenty of tholins at Titan. And then when Horizons got to Pluto, we see all this red gunk all over Pluto. We're like, well, we know that's not iron. What's going on here? And so it's tholins. So what's happening here? It's yet again, it's methane. Methane is the troublemaker here. What's happening though is that methane's just hanging out in the atmosphere. It's just minding its own business in the atmosphere. And then irradiation from our own sun can go way past Pluto. That's how powerful our sun is. All that radiation in the atmosphere just smacks these poor little methane molecules together. They get irradiated and they break apart and link back together and break apart and link back together. And then it's like a mess of Lego bricks. It's like if you were trying to build something blindfolded and without instructions, without even looking at the box beforehand, and you're just trying to build Lego bricks. That's pretty much what tholins are. It's just all these molecules just bumping into each other and linking together, and it just becomes these chains and chains and chains of organic molecules. So tholins, this is what happens on Titan very, very much, is that you have your molecular nitrogen and methane, and then ionization versus dissociation. So it's truly just bringing together and pulling it apart consistently. And then trying to make them in the laboratory is very dangerous, but it can be done. So quite a few labs in the nation are tasked, are funded to create tholins, or at least tholin organic material in the laboratory setting, because we don't exactly know how organic these things are. It's still very new to us. So ice geology in general, this list can go on for a mile. So this is just a very condensed list of what's considered ice geology. So you got polar caps, like the beautiful polar cap here on Mars. Different kinds of craters can be formed by different kinds of ice. You got mountains, frosted dunes are also very pretty on Mars. All this little blue speckly stuff, this is the South Pole of the moon. There's actually spots, craters on the moon that get just as cold as Pluto. Yay. You can have glaciers, you have cryovolcanoes. So specifically with the outer system, though, you get even slightly weirder geology. You can get what's called fluted craters. So this is an example of what a fluted crater is. So you get some sort of weird erosion that makes the crater kind of well, fluted, but kind of almost like a skirt. Multi-ring craters, again, mountains, different kind of icy dunes. You know, we consider dunes to be sandy. You go to the beach, you just see dunes everywhere. It's just, the sand is everywhere, but you can get dunes that are just ice, and those are very fascinating. Frozen lakes, and lo and behold, cryovolcanism. So again, most of what I do is looking at the geophysics, the rheology, the bending or the breaking of the ice. So how viscous are some of these flows, or do they just sublimate away, and or do they evaporate and they leave behind some sort of residue? Are they seasonal, or are they erosional processes? So real quick about cryovolcanism. So cryovolcanism, it's really fun to say, and it still does not, to this day, have a very clear definition. We had a meeting in Houston back in 2018, all about just bringing all of us together and just to chat about cryovolcanism. And specifically for a whole week of a meeting, it was like, okay, we got to define this. We got to define like where we're at with cryovolcanism. Where are we at with our research, and what more do we need to do? We never answered that question like at all. If anything, we left that workshop with even more questions than answers, and it's great. Hopefully we'll have a round two at some point in the future, but if anything, we left that conference with so many more questions, because we then realized we really don't understand cryovolcanism all that too well. And it depends upon who you're talking to as well. You consider random bits and pieces of like domes. The one here on the left is from Ceres, the one here all the way on the far right is on Europa, and those are little salt domes popping up. That's considered cryovolcanism. But then you look here at Enceladus, and those are geysers, those are plumes. That's also considered cryovolcanism. You could also have very big mountain structures that we would potentially see on Titan and a little bit on Pluto. That's cryovolcanism. So you have all these different flavors of cryovolcanism. But then you're also dealing with different kinds of ice, which means you're also dealing with different kinds of transportation of these ice and then salt. Oh goodness, salt makes everything weird. But salt helps make everything slushy. So very much like a giant 7-Eleven slushy machine in this case. That salt really helps lower the freezing point of your ice. But then it's still a matter of it's not just the churning. It could be churning. It could be your solid state convection. You could have ascension of warm ice. You could have partial freezing. You could have melt lenses, which are very odd to deal with, because melt lenses, you would have like little ponds of liquid that would be buoyant eventually or bubbled up upward. What, like exsolution? Exsolution means bubbles. Sometimes those melt lenses go over, they could be really tiny, they could go over large regions, or you could also have an entire ocean ice interface, which means you have your whole global icy ocean. Not very many moons have this global ocean, but some of them do. And it can get, again, it can get weird. So let's take a tour of some icy bodies, or how I like to call it, pretty picture time. So we're going to start with good old Ganymede and Callisto. Unfortunately, these two moons of the Jovian system, and when I mean Jovian, I mean around Jupiter, they're unfortunately very ignored. So sad. So Callisto is this small one off to the left here. So Callisto, it just looks like a shiny disco ball, and that's about it. I mean, there's not a lot of work has been done with Callisto, unfortunately. Ganymede has gotten a lot of very pretty pictures as of late, especially with the Juno orbiter currently going around Jupiter. It took a nice wide angle view of a couple sections of Ganymede fairly recently. I believe that was just a couple weeks ago. And there's going to be a Ganymede textbook coming out, I believe, early next year. So, woohoo. But just some pretty pictures of Ganymede, though. So Ganymede has all this kind of ropey terrain. And then all these kind of dark splotches. You have this bright ice going on here. So this is part of what would have been a impact crater at the time. So you have some sort of impact, and then whatever got excavated just went outward. So all that bright ice is considered very fresh, very, very fresh excavated ice. But all these like dark lanes all over Ganymede still eludes us, because it's just lanes and lanes and lanes of dark and light material. And they could be very different. The dark material is considered to be clay. It could be kind of organic, but Ganymede doesn't really have an atmosphere. So it's not necessarily tholins. Tholins, you need an atmosphere, but there's just some sort of irradiated gunk of ice making that the dark lanes. And here's another example of some of this ropey terrain stuff. So it's just pure chaos. Whoa, dear. Well, don't know what I pressed. I apologize for that. So skipping. Ganymede. Okay, and then there's beautiful Callisto. So there is one fabulous feature in Callisto. It's called Valhalla. So if anybody out there is a Thor fan, here's Valhalla. Or anybody who's in love with Norse mythology in that case. So Valhalla here is a multi-ring basin impact, which means this impact happened as such a sheer force that it actually rippled the ice over and over and over again around it. So here you would see the impact, but all of these ridges all the way out to here are just individual rings of the ripple effect from that crater. So big impact. So onward to Europa. So Europa is pretty. It will have a mission coming up, and I will get to its future mission here in a bit. But Europa is also pretty weird. It has all of this kind of reddish gunk as well, but in this case, it's cross between a little bit of tholins, but mostly salt. Salt in this case can have that kind of a reddish hue and just some sort of organic work here. But an interesting formation on Europa is all this like fish scale looking textures on the surface. And what this is that Europa self-heals itself. It's almost like its own superpower on this moon, where you have some sort of impact. Impacts don't necessarily stay preserved on Europa because the water, its global ocean inside is still so dynamic that if you were to puncture it, almost like a puncture wound, it would immediately scab up. So all of these little fish scale looking textures all over the surface are its scabs, or its battle wounds, if you will. So it's so interesting to see it just kind of how dynamic the ice is to self-heal its surface. So back to this image, though, all these little domes that you see here, also these little pimples on Europa here, though. So all this is like little salt domes. And we have salt domes here on Earth. And so a lot of people who study salt domes on Europa actually talk with people who study salt domes here on Earth, and we constantly have to talk to each other and go like, okay, how are salt domes formed here on Earth? Well, I don't know, we're still trying to figure that out too. So it's a really nice collaboration to go like, okay, how do they form here on Earth, and can we make inferences on how do they form on Europa with it completely icy and salty mixtures. So skipping right over to the Saturnian system, we're going to start with the largest moon of Saturn, which is Titan. Now, Titan takes the crown of it being a very unique moon. It's the only moon that has very large lake systems. You have beachside fronts, you have an atmosphere, you have climates and microclimates, and you have seasonal rain on Titan. Now, it's also 92 Kelvin, so you're dealing with negative 300 some degrees Fahrenheit. What in the world could possibly be liquid at those low temperatures? So water is very much a solid ice at Titan. So cross that off the list. It's not water ice. So in this case, it's actually methane. So methane acts just like liquid water that we would have here on Earth. So just remembering the water cycle here on Earth, you have a lake and you have some sort of heat. It evaporates, it forms clouds. The clouds move. It rains over a dry surface, and then back into the lake system, and then there's your water cycle. Same thing happens here on Titan, and it's so cool, except just really low temperatures. We have liquid methane lakes, and I mean big lakes on Titan, and they evaporate, they form clouds, they move around, it rains methane very slowly, and then it fills up those lakes again. And it has this kind of climate and seasonal process on Titan. Now, with the rain and how does liquid methane even work at those low temperatures? That's the beauty part of experimental work. We still don't 100% know what in the world is going on with Titan. Titan also has, besides its very weird atmosphere, it also has just weird geology too. So it has ice dunes. So all these weird black stripes or anything, it's not your computer messing up or anything. All these dark black lines here are dunes, except it's not sand in the case of silicate, quartz, grains that we would have here on Earth, but sand in the sense of it's all ice. It's all little ice grains that are piling up and moving along and making these dunes. This is my favorite. These are called labyrinths. So labyrinths are also a weird geologic feature. Now, whether they are erosional features or tectonic features, that's still to be determined. I'm also on this team to look at labyrinths on Titan. So imagine if anybody out there is a Game of Thrones fan, everybody's aware of like the giant ice wall in the Game of Thrones universe. So imagine, if you will, that very large ice wall, but in a maze, in very much maze-like components. That's pretty much what these labyrinths are. They're just very large ice walls that form these mazes, very patchwork all over Titan. But how they're formed, why are they formed, where they are formed, and if they're tectonic or erosional, still to be determined. So woohoo. And then you have Magic Island on Titan. So like I said, all this dark area here is your liquid methane oceans. These are two separate pictures. And there for a while, we just kept seeing this little bright feature. It wasn't there before, and then it pops up, and then it disappears, and then it pops up again. Like, what's going on? What is going on? And it took us a while. Now, this is from the Cassini mission, but it really did take us a while to realize, oh, that's an island, and it gets flooded. Okay, so that means that the lake actually gets filled with liquid methane to a scale that it floods islands, and then it subsides, and then it floods and subsides. All right, onward to Enceladus, a lovely, very active ocean world around Saturn. So very much a cousin to Europa. A lot of people compare Europa and Enceladus. Very similar. You get a lot of craters, at least in the northern part of Enceladus, though, but the southern part is where the party is at. So the southern part, you have this really pretty light blue, tingy looking stripes, and we actually nicknamed these the tiger stripes. The official name are called sulky, and that's kind of a weird Latin name for trough, but I like tiger stripes better. So all these tiger stripes are just so fascinating because they're alive. It's so weird to think about this, though, but essentially what happens is that the ocean with Enceladus is so dynamic, and it's churning and churning and churning. Now, why it's churning, how hot it is, how active is it with hydrothermal vents? We're still hypothesizing about that. It's all still theoretical. We'd like to, believe there's hydrothermal vents in here, and maybe there's like some bacteria that would, love to be in the oceans of Enceladus. All right, sign us up, let's go. But back to these tiger stripes, how these operate is that you would have these stripes essentially kind of heave open. It's almost like it's breathing out. And so as they just open, even just for a little bit, it has so much pressure of vapor and hot gas right at the surface until it just opens up just a little bit, and then poof, there goes the vapors. And so Cassini was just about to do a really close flyby of Enceladus, and one of the tiger stripes opened up to give us this fabulous image. But there for a while, we did not confirm just quite yet what these plumes were made out of. And so there was a bit of hesitation with Cassini. It's an orbiter. You can't slow it down. So if something happens to it, it happens. So we're coming right at this plume, and we're like, well, hope it survives. We're gonna find out. It's gonna go, whether we want it to or not. But we turned on all of our chemical spectrometers and cameras and everything. We were ready to essentially sniff, and sniff we did with this vapor plume, though. So what we were able to find out was that not only was it really warm and it was water, but also it had the same salinity, which means the same amount of saltiness as our own oceans here on Earth. And that's just absolutely fascinating. So all these different kind of tiger stripes. Now, why these tiger stripes are only in the southern part of the moon? Why don't we see them everywhere? Why don't we see plumes everywhere? You're dealing with tidal interactions with Saturn, and you're dealing with different kinds of ice. To have that kind of warmth, there you're dealing with high pressure, high temperature ices at this point. But the why, we're still trying to figure that out. So it keeps us busy, if anything. Now I'm going to go through like some of the lesser known moons of Saturn, but if you do know about these moons, good on you, gold star. So just some really pretty pictures nonetheless. So this is Iapetus, which is the walnut moon. It has a very interesting dual personality, if you will, of the darker regions, potentially tholins that may have just rained onto its surface. Not entirely sure yet. And then also the lighter surface there, but that equatorial ridge to make it look like, its nickname, the walnut moon, is still to be determined. Is it a mountain range that has formed from the inside out and it just pushed its way out? Is it two worlds that collided and then it just kind of squished in the middle? Or did it have a ring of debris at one point? Was it like its own like little mini Saturn, and the ring just kind of collapsed onto the surface and it forms a ridge? So those are the different kinds of hypothetical flavors of that ring. You have Hyperion, the sponge moon, or the potato moon. I think we prefer sponge moon. So all of this is this very, very porous, spongy ice. So Hyperion is really tiny moon, but so weird. Helene is a beautiful moon. You have all of these almost glacial looking flows. So you would have almost like a plasticky, slow, smooth rheology physics with the ice moving on here. But Helene, again, is a really tiny moon, but very pretty flows. Now, I'm not going to spend too much time with the moons of Uranus and Neptune here, though, but I just wanted to give a quick shout out to the moons of Uranus. They're still just as weird with a lot of tectonics. So you have these huge fault systems that would have just cracked the surface. You have these what looks like Dorito pizza wedge looking blocks of ice here. But what's interesting about these blocks of ice is that they essentially just kind of squished. They didn't just form there. They would have had to be broken apart, almost like glacial style, and then just kind of sunk slowly into its ice. And Miranda, oh my goodness, Miranda is a train wreck of a moon, and we nicknamed this the Frankenstein Moon for a reason. So this poor moon has been potentially just obliterated, but not too much where all of its pieces can just free flow around. Obliterated enough to just kind of go out and back in. It like pretty much just try to paste itself back together. Didn't do a pretty good job, but it's still pretty. So I'll give it credit. And then Triton. So Triton is a very fascinating moon. I fully support us having a future mission to Triton. I believe that we absolutely need a future mission to Uranus and Neptune at some point. If we had to choose one or the other, I am all for Neptune and Triton. So Triton is essentially what we consider a cousin of Pluto. It would have originated somewhere in the Kuiper Belt system, and then it got captured by Neptune. So it's not a true moon of Neptune. Instead, it is captured. So we do call this a captured or trapped moon. It's going into a backward orbit around Neptune. So give it a couple thousands of millions of years into the future, and Triton will eventually smoosh right into Neptune, though. But don't put it on your calendars anytime soon. So Triton, though, what we consider to be the cousin of Pluto is because the ice is fairly similar. but the geology is very different. So we have all this kind of wibbly wobbly looking ice here. Back to this, a lot of these dotted looking plains here around this hemisphere, we call this the Cantaloupe Terrain, because if you ever looked at the skin of a cantaloupe, that's pretty much almost everywhere on Triton as well. These are potentially some cryovolcanoes, but again, when you think volcano, you think mountain and fire and smoke and everything. No, not necessarily. Again, what I talked about before, where you can have like little domes, or you can have geysers or anything. In this case, you have puddles of cryo lava. So there's a potentially a little vent there and a potentially a little vent up there. And what would have happened is that the ice may not have been so active. It may not have been churning enough to really be active. So what happens to the ice is that it would have just been buoyant, like a very, very slow lava lamp, to the point where as soon as it reaches the vent, it just kind of goes and it fills up the basins. Not exciting whatsoever, just kind of infills the pool. But what is dynamic is the southern hemisphere of Triton. So this is the south pole of Triton. But all these little black streaks. And we're like, okay, think about this. Voyager 1989 at Triton, and we get these images. And we're like, what in the world are those black streaks? What in the world's going on? Those are geysers. Hooray! There is some sort of dynamic thingy going on Triton. And it did take us a while to realize it was nitrogen. I only in the past 10 years, in the past decade, I believe, someone finally figured out the density of the eruptions, and then the nitrogen ice, and then how far the geyser would have taken. I believe they figured out like the wind velocity of these geysers, and it's like, I'm glad someone did it. Someone did the math for it. Good on them. So onward now to my favorite planet is Pluto. So Pluto, I did a lot for my PhD. It's a very fascinating planet of the Kuiper Belt system. So Pluto, though, we honestly did not expect to look like this whatsoever. We didn't expect the heart. We didn't expect anything geology related on Pluto. We legitimately thought it was just going to be kind of boring. It was just going to be cratered and ice. It's like, okay, hooray, we got images of Pluto, okie dokie. But New Horizons got there summer of 2015 and sent us back these images, and we're all like, oh my goodness, it's there's a bunch of geology, okie dokie, let's get right to it. And so all the questions then start pouring in as to like, okay, how does it have mountains? How does it have glaciers? How does it have cryovolcanoes? How does it have some of these very bizarre geology? And then it goes into the questions of the what and the why. Why do we only see mountains in certain parts of Pluto? Why do we only see the cryovolcanism on the southern part of Pluto? Why do we only see the heart? What's on the far side of Pluto? What's on the backside? So it's so fascinating. So looking at this again, so keep in mind the most of the ice on Pluto is water ice, but with hints of nitrogen, carbon monoxide, and methane. So you're dealing with all different kinds of ice, but they're very basic ice. This is nothing exotic, nothing with like a 20 character exotic name of ice, named after a giraffe. I don't know. These are very, very simple ices and very simple chemistries, and yet they give us the most random geology on Pluto. So we call this Tartarus dorsa. This is the Snakeskin Terrain. Now, once we saw these images, and I remember seeing these images and talking with other fellow Pluto people who were like, what's going on here? It's a very weird texture. It's almost like someone took you ever do like sponge painting and it kind of gives that kind of texture. I don't think there's some cosmic sponge that kind of sponged that area of Pluto that we were aware of. So it's like you have these very spiky, and I mean spiky, spiraling towers of ice at an angle. turns out we actually have these on Earth. Lo and behold, where in the world could these possibly be here on Earth? Turns out they are around the Atacama Desert. We call these penitentes. So penitentes, just to give you a scale, I'm about 5'7.5". These are about my height or less. So you could actually stand up to some of these, or at least, don't sit on them because they're very spiky. But how they're formed is just you got to have the right angle and the right density of ice to then have it sublimate in a certain way, and the sun hits it at a certain angle and it makes all the ice spiky. Now, what's weird about Tartarus dorsa, though, is that it's only found in one part of Pluto. It's only found right here in the eastern hemisphere part. So why isn't it everywhere? Still to be determined. You also have some very blocky mountains here. We call this chaos terrain. Chaos terrain is actually found very common along all sorts of icy moons, and we just happen to see more chaos terrain on Pluto. Now, chaos terrain is a geologist's lazy term to say mountains crunch together and it's chaos. That's essentially why we call it chaos terrain. Now, why the mountains here are very blocky and bunched together and clashing against each other, it's very chaotic. Again, we don't know, to be determined there. But something also fascinating about this is that you see a little itty bitty lagoon here, a little bitty lake. And what that tells us is that all of this textured material off to the right here, this is part of Sputnik Planitia, this big basin, the heart of Pluto. It's still alive. It's still very viscous. It's sticky. It's moving. It's churning. But seeing a little bit of that over here means it's going under these chaos blocks and just kind of popping out. You have Barre Montes, you have Hecla Cavus. So Barre Montes, I won't get into too much detail here though, but Barre is this poor innocent glacier, got ripped apart and then it squished violently into the water ice beaches of, on Pluto. And so what happened then is the very thin top layer of this glacier is methane, which is a very brittle ice. So that poor methane layer was almost like an accordion. It just got squished and then rippled from the effect. So Montes meaning mountains. So all this dark material here is all that methane rippling, which is cool. You also have these big fault systems that have cracked open bits and pieces of Pluto. And then here's our fabulous, one of our fabulous cryovolcanoes. The other one is in shadow all the way down here. That's Picard. This is Right Mons. So Right Mons, all of this weird knobby terrain is what we call this. All these knobs here might have been part of its lava that would have just kind of bubbled and pillowed out of this cryovolcano. So very fascinating stuff. Real quick about Charon, which is Pluto's moon. Anybody out there a Lord of the Rings fan? This really dark polar region of Charon is named Mordor. So we love our references. So again, just really weird ice, all these big canyons of ice. You also have this poor little mountain here is actually sinking into the soft ice, very, very much like a Lego brick in the Play-Doh at this point. So Pluto System After New Horizons is the newest book out from the University of Arizona Press. So if anybody is interested in the dynamics of Pluto, the physics of Pluto, the geology, the chemistry, everything, all the science of Pluto since New Horizons, the book is now available. And then some exciting missions coming up specific to ice. We have the Artemis mission to the moon. And there's also a couple smaller lunar landers and rovers preceding Artemis. But Artemis is going to specifically go to the South Pole of the moon and hopefully and safely excavate some of that ice so that we can figure out what in the world is that ice even doing at the moon in the first place. We also have Europa Clipper. Hooray, Europa Clipper. Europa Clipper has been a mission in the works for quite a few years. It just got selected for its who was going to launch Europa Clipper. So the bidding has just been won not too long ago. So they have a rocket now. They have a ride. They have a ride into space. So hooray, Europa Clipper. And then we have Dragonfly. Dragonfly is going to be fantastic. This is going to be a mission out to Titan, out by Saturn. So Dragonfly is going to be this fantastic quadcopter-looking laboratory. It's going to be a laboratory with wings and legs, and it's going to hop around the surface. Not terribly much, not terribly high, but it's going to do science. It's going to be a flying laboratory. It's going to be great. Current research questions, this list can go on for a mile long though, but this is just some of the questions that we're still trying to figure out about just ice in general. Specifically, what's the conditions of cryovolcanism? Exogenic versus endogenic, which means what processes are happening at the surface from space weathering or from irradiation or from what's going on in the outside environment to influence the geology and the ice. Versus endogenic, what's happening in the interior? Is it hot? Is it hot cores? Is it spinning cores? Is it your tidal stresses? Is it buoyant pockets of salt and ice that is screwing things up? What about ice tectonics? We think tectonic plates here on Earth, but there could be tectonic systems on ocean worlds as well. So these are just honestly our current open research questions that we have at the moment with the outer solar system. But until then, we don't have definite answers for any of these. But thank you so much again for having me here tonight, and I'm happy to answer any questions you may have about cryogeology in the outer solar system. So thank you.
Oh, thank you so much, Dr. Ahrens. That was super cool. I loved all those pictures and learning about all the amazing science that you're doing. So thank you for sharing that. So it looks like we have actually quite a few questions here, which is great. All right, so I'm just going to go through and read them. So, okay, so this first one is from a user by the name of Bible Sisters. So let's see. They're asking, does the movement of plate tectonics rely on a molten core with a solid center? How does that work with an ice-based plate?
Good question. All right. So as far as what happens here on Earth, yes, we have a very dynamic core. We have a dynamic mantle. We call this a convection belt in a sense, where the mantle churns and the plates just kind of glide along. Now, with icy plates, you don't necessarily have that big churning mantle. You can have a dynamic core all you want, but does the mantle churn globally, or does it just kind of go in spats and spurts every once in a while? It could not even be dynamic whatsoever. You can have what's called remnant ocean worlds, which means the ocean is dormant or otherwise dead, very crystallized. But dynamic worlds like Europa and Enceladus, we'll use that as examples. So those ice shells and the geysers and very dynamic surfaces. So we consider them to be very tectonically active, but not with large continent-looking plates. But there's different kinds of definitions here, but we call them ice shells. So whether these shells are considered stagnant lid shell, which means it's just one shell and the shell is actually just kind of bending, or you have a kind of broken shell dynamics, which means you have, again, not continents being broken apart, but just these separate dynamic areas of the shell that are working not in tandem with each other. So having those different flavors of ice shells is still being a debate as to, what's the definition of that for Europa and Enceladus. Do any of those apply to Titan? The unfortunate part about Titan is that we only got so much data from Cassini, but not enough. So is Titan very dynamic, or is it just kind of like, it's there? We don't know.
Cool, thanks. All right. So we've got several more. So, all right, so Bible Sisters is busy. So I have another, actually a couple more questions. Okay, so the first one is that the same kind of methane? And I'm not sure quite which part of the presentation this is referring to, so maybe you can guess from context clues. They're asking, is that the same kind of methane that NASA found on Mars that they think could indicate some sort of organic life?
Oh, gotcha. Okay, yep. So like some of the methane bursts that we've been seeing on Mars, same methane. I mean, methane is methane, and that's the beauty part about it. So same thing like water ice, it's still H2O. In this case, methane in a vaporous form, yeah, it's still very much just one major carbon atom and four hydrogen atoms. You got your CH4 in a vaporous form. Same thing that we would have methane in clathrates in Siberia. It's the same methane, but the dynamics are different. And the environments are hopefully different as well, Earth versus Mars. So why methane would have bursted like that, and why in that area? And was it clathrates just popping, or was it organic? Which is entirely possible. There are certain types of bacteria called methanogens that could survive on Mars. They hate oxygen. Great. They love Mars. There are a few laboratories in the nation that are specifically looking at methanogens, very interesting critters, but they essentially burp out methane. So could it have been these methanogens just singing out methane in that one moment, and we just happened to get it? Or is it volcanic? Is it something that's been trapped in the lava and it just happened to be exposed and it went poof? So debates are still going.
That's really interesting. Biosignature stuff is so cool.
Oh yeah, but oh my goodness, we have a long ways to go.
Yeah.
If anything, we've barely scratched the surface on biosignatures with our own planet, and I think that's what makes astrobiology extremely difficult, but extremely fascinating. There's a lot to do here on Earth, and then apply it to other planets.
Super, super neat stuff. Okay, so next question from the same person. What is the colorization of these pictures based on? Is that a specific chemical mix?
I'm going to assume it's the colors of like the Pluto, the reds and yellows. Yeah, Pluto isn't that multicolored. Yeah, so the warmer colors are typically the higher concentrations of whatever chemical that was. So the heart of Pluto is very much reds and yellows in nitrogen and carbon monoxide. So you get a larger concentration of those ices with the heart. Everywhere else is a lot of methane and water ice.
Neat. Okay. And again from Bible Sisters, when you say that the ocean in Enceladus is warm, is that relative or is it like Earth-like temp or Earth temp warmth?
Earth temp warmth, yeah. So we were very surprised that it was like Earth temp warmth when Cassini flew those geysers, and it was like, oh my goodness. So not only are you getting liquid water at Earth temp warmth, tepid, but the same salt content as our own oceans. Is like, yes, this is great. And it was that moment that we're like, oh, this is awesome. What do we do about this? All the questions just start pouring in at that moment, and we're still trying to answer a lot of those questions now. Cassini, unfortunately, it's been a dead mission now for a couple of years. Rest in peace, Cassini. But we're still dealing beautifully with all that data. And Dragonfly is going to give us a lot of cool data. I believe that mission is to be launched in 2036 or 2037. So got a few years.
That's really amazing. Yeah, just to think about flying through something that's wet and Earth temperature, like out in the middle of space. That's just really cool. Okay, so and this is a question from Haley Wall. She says, "Amazing talk. Besides Pluto, do you have a favorite icy body?"
Oh goodness, besides Pluto. Oh goodness gracious. Let's see. As far as icy bodies go, Titan. Titan is just that weird of a moon. To be like, what is this weird geology? Especially the labyrinths. How are those even constructed? How are they that big and maze-like and everything? And the cool part is that we see those big mazes in Indonesia, of all places. We actually see them as karst. Karst meaning like cave-like limestone calcite caves, but they form those labyrinths. But you're not going to get limestone anywhere else besides Earth. What's going on here? So there's just something going on there that we don't know about, and those lake systems and having its own climate and weather systems. It's truly playing by its own rules compared to the other moons. So Titan would probably have to be my second close favorite. Icy body. Now, rocky bodies, I think Mars is pretty cool. So
Neat. That's cool. I've always thought Titan was amazing. Okay. Let's see. So Bible Sister says, thank you so much for answering my questions. I loved your talk. Thank you for all your questions. Those were super questions. Okay, Elijah Williamson says, how did you get started at NASA?
A good question. All right. So it was honestly just a tumble of happenstances. I was chatting with Ellie before the live stream, though. I was originally a radio astronomer for a couple years, and I just stumbled onto an internship down in Arizona to do Mars Global Surveyor data analysis, and immediately fell in love with planetary. So that's where my love of Mars comes from. Is that was the first planet I actually got to work with data for. I look back at it now and go, I'm like, man, that was actually kind of a boring data set now that I think about it. But you know what, Mars is still cool. And so I went to Mars conferences, and I went to one Mars conference in particular out in California, met my PhD advisor there, and he had me work on Pluto for my PhD. It was right as soon as New Horizons got to Pluto, so the timing was perfect. And then met with my now postdoc advisor, just talking about ice. And we were pretty much like, you know what, there's ice on the moon. Let's do some physics and thermodynamics with it. So that's what I'm here for, is just kind of evolved from planetary to specifically doing ice. But most of my job is just planet hopping too. I've done work on Ceres, the dwarf planet in the asteroid belt. I have done some Titan work. I've done all sorts of Mars. I just finished a Ganymede project as well. So I'm kind of all over the place with the solar system. So how I ended up at NASA is honestly just, I reached out. I just honestly just contacted my postdoc advisor and was like, hey, let's chat about ice. Oh, like the nerd that I am.
Yeah, that's great advice. So don't be afraid to share your nerdiness with other people. Always
exactly, because we're all the same in different levels of nerdiness, though. But if you're interested in something, if you really want to, even if you're not looking for a postdoc, or if you're not looking for a job or an internship, you just want to chat with someone, email them. It's perfectly fine. Or you're like, oh, I just read a paper, I want to know more about it. It's perfectly okay to email that person and go, hey, I just read your paper, I want to know more about it. Have at it, because it's, if anything, it's your curiosity that you should follow through with. You shouldn't have to sit around and go like, oh, maybe I'll figure it out later. I don't think that person will talk to me. You never know where it's going to lead you.
That's great. Thank you for that. And Elijah says thank you as well. All right. So I think that's the end of the questions in the chat. I had one, and then I'll let you go because I know we're getting a little bit late here. So I know I've heard that a lot of planetary scientists, spend time kind of visiting like analog environments on Earth. Have you done that? And if so, what's your favorite place?
Oh goodness. So I've done a little bit of that. I was while I was still out in Arizona, we visited some dunes out there, because that was mostly what I was doing out there, was looking at how do dunes form on Earth, and then there's a bunch of different kinds of weird dune structures on Mars. And so seeing them up close and just seeing how like the wind would have carved out these rocks, and how it would have made different kinds of, not to make it sound boring or anything though, but how to make weird sand piles, how to make different shaped sand piles. And guess what? There's different kind of weird shaped sand piles on Mars. And so again, seeing them up close and just seeing honestly how big these were, I did not expect the scale of these enormous sand dunes in Arizona. And then for planetary scientists to tell me, oh yeah, these are baby dunes. The ones on Mars are way more massive. It's like, okay then, I'm convinced. Okay, you got me hooked. So doing field work out there was absolutely fantastic. By all means, I wish I could do more field work. Unfortunately, that's very difficult nowadays, considering the time. But back then, and hopefully in the future, there's a lot more to be done with certain areas around the world to make us learn about planets.
All right, well, that is fantastic. Thank you so much for answering all these questions, for taking all that time. It's just been great having you, and we are just super lucky to have gotten to have a bit over an hour of your time. So,
yes, thank you. And that was good advice too for students. If they have questions, always, follow your passion and reach out. Perfectly fine, acceptable thing to do. Absolutely.
Yeah, and if anybody has any like other planetary questions in the future, or you just want to know more about planetary science, feel free to email me. You may, it's easy to just Google my name and my email will pop up. So, so feel free to email me as well.
That's great. Well, thank you all so much for coming. Thank you again, Dr. Ahrens, and we'll see you all again next time.
All right, thank you so much for putting this program on. It's so exciting, and I'm so glad that you're doing this program.
So thank you again, and everybody, hope you have a fantastic